Chapters 2 and 3 are our chemistry units. In Chapter 2, we'll do an introduction to chemistry. We'll talk about chemical reactions, types of bonds, and properties of water. And then in Chapter 3, we're going to focus on biological molecules. So those types of bonds are going to be really important in Chapter 3. Our learning objectives for Chapter 2 include knowing and being able to describe the parts of an atom and to make a labeled diagram of a carbon atom. We will be doing the carbon atom in class, but there are examples of labeling in this video. You need to know the 4 different types of bonds: ionic, polar and nonpolar covalent, and hydrogen bondings. And then we are going to talk about the emergent and biologically important properties of water and talk about the pH scale, acids, and bases. So why do we study chemistry? Obviously, you are here for biology, but remember from Chapter 1 that in biology we are often looking at a reductionist view of biology. And that means we need to get down to the most basic parts. And when we do that, we see that foundations of life are found in chemistry and physics, and that life is actually bound by those physical and chemical properties in order to sort of continue on and proceed with things as usual. So emergent properties are really important, looking at how things function differently when they're together than when they're in their parts. And then, of course, reductionism, understanding how those parts work, understanding what they do, how they interact in order to get those emergent properties. So any lecture on chemistry is going to start with the periodic table. We're not going to talk a lot about this periodic table, but it's important because we can see some of the molecules that we are worried about. We're really worried about hydrogen, carbon, nitrogen, and oxygen. And there's some important information that we can get from the periodic table that we will see in a little bit. We can get the weights of those atoms, we can deduce the numbers of the parts of those atoms, and that's going to be really important when we're talking about the bonding. Just a couple of trends as we go left to right and top to bottom. The weights increase, so the molecular weight of these atoms increase. And then if we're looking at this right side over here, here we have increasing, not go quite that far, increasing in electronegativity. So that is sort of the attraction that it feels for other molecules. And that's going to be a really important concept when we get to our different types of bonds. Now, before I move on, I do want to say that this set of videos tends to be long, no matter how hard I try. They're always a little bit on the long side. I do apologize for that. I promise I'm not trying to cram so much information that you can't take it all in. But I will say that there's a lot of things, especially in the beginning of this chapter, that are simply definitions. It's going to feel like I'm reading from the slide because I really am. You might just need to make some flashcards and just sort of deal with the information. And as I need more explanation, I will slow down and provide that. So let's start our chemistry discussion with atoms and molecules. So elements are any substance that cannot be broken down further by chemical reaction. Now, elements and atoms are often used interchangeably. So the previous slide showed all of the different elements, and often a single piece of those elements is called an atom. Sometimes those elements sort of prefer to hang out in pairs, things like that, but a single individual part is called an atom. So atoms and elements are sort of interchangeable. They are single units. So one oxygen atom is also the element oxygen. Now, the reason that we are worried about elements is that about a quarter of the elements are essential. That means they are required for life. So you have to have them for the organism to live and to function normally. And you start to have problems when these elements are not available. Now, you're probably really familiar with oxygen, carbon, hydrogen, and nitrogen. Those make up 96% of our body mass. So the majority of our bodies, of any living organism, are going to be those four elements: oxygen, carbon, hydrogen, and nitrogen. The reason is that a lot of our living organism weight is water, and water is made up of oxygen and hydrogen. Then we also have these trace elements, the second column down here. These are things that are needed in lower quantities, but are still required. So you can see that all of these other ones combined equal the same amount as nitrogen. So we don't need nearly as much, but we do need some of these. You might notice that some of these are vitamins, calcium, phosphorus, sodium. Sodium is not a vitamin. Calcium, phosphorus, potassium. Those are all vitamins that you're probably familiar with, and they're required for normal functioning. When we look at the air around us, we again see those four, the four elements, oxygen, not hydrogen, oxygen, carbon and oxygen and nitrogen in the air around us. So these four are ubiquitous. They're everywhere, and they're really important for living things. You probably know that you breathe in oxygen and you breathe out carbon dioxide. That's essential for life. So these elements are really important. They're the basis of all our biologically important molecules, and that's why we start with our atoms and elements. Now, because we're going on and on and on about emergent properties, we see them in the smallest entities. So when you start to combine elements, you produce a compound. So a compound is a substance that is made up of two or more elements. And when you have fixed ratios, meaning basically the same recipe, you always get the same compound. And what's important about compounds is that we see emergent properties immediately at the lowest level of chemical organization. We start to see emergent properties. So for example, we have down here on the bottom sodium and chlorine. So you're probably familiar with these just from sort of daily life. Now, sodium is highly flammable in its pure form. Chlorine is a poisonous gas in its pure form. But when you combine them together, you get sodium chloride, also known as table salt. Now, obviously, table salt is not explosive, nor is it poisonous in the right quantities. You eat it all the time. In fact, you probably eat too much of it. But you can see that we have different properties when those two molecules come together. So let's move on to atomic structure. What is the structure of all of these elements? What are the parts? What are they made of? So atoms are the smallest unit of matter that retains the property of an element. You know, that's a little bit tricky wording. You can go with atoms are the smallest unit of matter. That's fine for biology, maybe not fine for chemistry or physics, but that's what we're going to go with here. So atoms and elements use the same symbol, and here we have a blow up of the periodic table image from the first slide. You'll see this is carbon, nitrogen, and oxygen again. Carbon's atomic number is 6, nitrogen 7, oxygen 8, and then we have an atomic weight here for each one of those. We'll talk about what those mean in a second, but that periodic table does give us some important information. So if we're talking about an atom, it always has a specific symbol. The only ones that you really need to memorize for our course are C for carbon, N for nitrogen, O for oxygen, and H for hydrogen. Those are pretty easy to remember. You probably don't even need to make flashcards for that. All right, so our atoms actually have smaller structures that make them up. Those structures are called subatomic particles, and there are 3 types of subatomic particles. The core, or the nucleus of the atom, is made up of protons and neutrons. And they are called this because we're referring to their charge. So neutrons are actually neutral. They have no charge, but they do contribute a lot of weight to the atom. Protons have a positive charge, and they are important for attracting negatively charged electrons. So the nucleus is made up of these protons and neutrons. You can see here that we have 2 neutrons and 2 protons in this atom, and they make up that core or nucleus of the atom. Now they take up most of the weight of the atom, but they take up very little space. And the reason is that the rest of the space is empty, and it's actually sort of a cloud of electrons. Now you might be thinking, there's 2 electrons here. How do they make a cloud? Well, the reason is that they're constantly moving. They're shown as stationary here on the left, but on the right, but on the left we actually see sort of a cloud, and that's because electrons are constantly moving around the nucleus. And they're moving so fast that if they were large enough to see, we wouldn't be able to see them. It would be like a fly just constantly buzzing, just buzz around the nucleus, right? So atoms are mostly empty space. They're the empty space where basically in the cloud where the electrons are not. So we have a lot of weight in the middle, a lot of empty space around the nucleus, and then we have electrons sort of buzzing around this shell around the outside. So let's go back to this atomic number and we'll talk about what that actually means. So here we have helium. A few slides ago we had carbon, nitrogen, and oxygen. And this box on the left represents information that we would find on the periodic table. The number that is always shown on top is called the atomic number. Now the atomic number is going to be the total number of protons. So the page before, we were actually looking at helium. Any atom that has 2 protons is going to be helium. Its atomic number is 2 based on the number of protons. So if you have an atom that has 2 protons, it's going to be helium. Now those protons reside in the core, and also in the core are the neutrons. On the bottom, we have the mass number. So this is the weight of the atom. And it is called, the weight is measured in something called Daltons. And we list the weight as atomic mass units. So our mass number is going to be measured in Daltons. This mass number is going to tell us the total weight of the protons plus the neutrons. So our total weight is 4.003 atomic mass units. Now we can use the information in the atomic number to help us determine how many neutrons there are. Each proton and neutron weigh approximately 1. So this means we have 2 protons. So we have 2 neutrons to get an atomic weight of roughly 4. So our mass number here is going to tell us that we have 2 protons determined from our atomic number plus 2 neutrons to equal our mass number of 4.003. Now, I realize that it says 4.003 and I'm telling you 2 plus 2 equals 4.003. This just happens because Daltons are approximately 1 atomic mass unit. When you get into the quantum physics of all of this and the actual weights, they vary slightly from 1. Again, we're biology. We're just looking for the general idea here. So we're going to just estimate that 2 plus 2 equals 4.003. You might also see the atomic symbol written slightly differently. Over here we have sodium. This is just a different way to write it without drawing out the atomic mass information. The periodic table information. In this case, the atomic number is on the bottom. So this is going to say that we have 11 protons and the atomic mass is on the top. So 23 minus 11 is 12, which means we have 12 neutrons. So the weight is approximately 23. In order to get a weight of 23, we actually need 1 more neutron than we have protons. So we need to get to chemical reactions because we are going to be building biological molecules. That's our reason for studying chemistry. In order to get to chemical reactions and bonding, we need to learn about electrons. So remember that our atom is made up of an atomic core with our protons and our neutrons, and then around it, we have electrons that sort of buzz around. Electrons are the parts of the atoms that are actually involved in chemical bonds. And this actually should say chemical bonds, sorry. They're involved in chemical bonds. Now, it's the interaction of electrons with other atoms that allow for those chemical bonds. Electrons possess energy, so they are charged, which means they have energy in themselves. And when you move electrons, you are moving energy. And that's because energy is the capacity to do work or to cause some sort of change. And so when you're moving electrons around, you're basically moving or transferring energy. And because electrons are charged, they're storing potential energy, energy that can be used in forming bonds with other atoms. So when electrons are transferred, energy is transferred. So when we think about electrons, electrons have specific energy levels. And those energy levels allow the electrons to stay a specific distance from the nucleus, which creates sort of shells or energy shells around that nucleus. So as electrons move between different shells, they either absorb energy or they lose energy. So as they move farther away from the atomic nucleus, they actually gain energy and they have more potential energy to form bonds. As they drop in energy levels, energy is lost or energy is released. And so how far electrons are from the nucleus is really important for how much potential energy they have in order to form bonds. Electrons tend to be found in shells. Now I showed that on the last slide where we had the nucleus there, and then we have this sort of ring around the nucleus where electrons reside. Now, these shells like to be filled with pairs of electrons. And whether or not an electron is paired affects the chemical behavior of that atom. So atoms want their energy shells filled up in order to be more stable. But as you can see, hydrogen doesn't have a pair. It's only got one. So that means that hydrogen is going to want to form bonds. It's going to want to fill up that shell so that all of the electrons have a pair. So if we look at some of these other shells, let's look at neon here. Neon has 2 electrons in that first shell, and it has 8 in its outer shell. Now that is common. We had 2 electrons on the inner shell and potentially up to 8 electrons on the outer shell, and then any remaining shell can hold up to 8 electrons. Now neon has all of its electrons paired, so it actually doesn't really want to form chemical bonds. But if you look at some of these other ones, carbon, nitrogen, oxygen, they all have sort of unpaired electrons. Now you might look at carbon and say, well, there's 4 electrons there, don't they make pairs? Well, no, not really. Electrons want to be in sets of 8. Atoms want to fill their electron shells. And so carbon will actually form up to 4 bonds in order to get 8 electrons into that outermost shell. The outermost shell is the one that's important because the outermost shell is the one that's going to allow electrons to form chemical bonds. That outermost shell is called the valence shell, and the electrons that hang out in that valence shell are called valence electrons. And it's those valence electrons that are going to form chemical bonds because those electrons want to be in pairs. So these unpaired electrons in the nitrogen valence shell want to form pairs with other molecules. Now, if we're talking about these 4 sort of biologically important molecules, carbon, nitrogen, oxygen, and hydrogen, they tend to form chemical bonds with themselves. So we'll see when we get to chapter 3 that our large biological molecules are actually made up mostly of carbon bound to hydrogen with some oxygens and nitrogens in there as well. Oxygen likes to bind to itself. It also likes to bind with hydrogen. Hydrogen really likes to bind with other things because it's got 1 unpaired electron in its shell. Now those valence electrons give us the bonding capacity. That's just the number of bonds that an atom can form. So if we have 3 unpaired electrons, we're going to form 3 bonds. So our nitrogen picture over here, we've got 5 valence electrons, and by having 5, that allows one of them, one pair to be made. But these other 3 are available to form 3 bonds. If we look at carbon, we have 4 bonds available. Oxygen, we have 2 bonds available. Those are the bonding capacities of those elements or atoms. A couple quick things here because we're back on the periodic table. As you go top to bottom, you increase the number of electrons and the number of valence shells. And as you move left to right, you also increase number of electrons.